Hello, y'all. Welcome to lesson 63 of my DP chemistry curriculum. Today we're doing structure 3.1.9, which is an HL topic. We're going to talk about the formation of variable oxidation states and transition elements. We're going to explain that by their successive ionization energies and how those are close in value. Furthermore, we'll deduce the electron configurations of ions in the first row of transition elements, which is something we've already done. So we're going to do just a little bit of practice on that. So the question is, why do they have variable oxidation states? And the main reason is that they have s and d orbitals containing, containing valence electrons. And the thing about these s and d orbitals is they are extremely close in energy, extremely close in energy, such that when we remove electrons, we usually remove or ionize from s orbitals first. So just do a little review. If we look at, say, titanium, titanium has the electron configuration. I'm going to do our shortened one, argon 4s2 3d2. But titanium can also become titanium 2 plus and titanium 4 plus. And when it becomes 2 plus, it's going to lose those s orbitals first, so it's just going to be argon 3d2, and 4 plus is just going to have the same configuration as argon. So we lose the s first, then the d again because of that closeness in energy. As I mentioned earlier, we can view these trends with successive ionization energies. Successive ionization energy. So that's where we look at the ionization energy of removing 1 electron, 2 electron, 3 electrons, 4 electrons, etc. And so I took some pictures from the Cognity textbook. And when we look at vanadium, our transition element, and compare it to calcium, you'll notice that while the first two removals are pretty similar, calcium will jump up in energy, while vanadium stays on a pretty continuous trend all the way, which allows us to remove each successive electron a little bit easier. We can actually remove 4 electrons for less energy than the third electron of calcium. So as we look at these trends, and we can actually even look at one more, this is all of vanadium's, we'll notice that vanadium tends to have those 4s being lost first, followed by 3d, and you'll notice it's a smooth increase in energy before we get to our p orbitals, where we have that more sharp uh, change in energy. So the main thing that we're going to take away from this is that for ionization energies of transition elements, the energy difference between s and d orbitals is so small that they readily lose valence electrons from both. And that's going to allow for many oxidation states, or many different oxidation states. So that's the key thing here. Now, the other key thing that we need to just keep in mind is that different oxidation states of an element will have different properties. And we don't need to know the properties of each oxidation state. You just must understand that the different states will have different properties. We're going to explore these much later in our next section as we look at the um, colored complexes that transition complexes make with their different oxidation states. So I hope this helps, and have a great